Well, you did better than me. Oh, now when I try to close the program, it
Okay.
oh, sick. It's almost like it started with some initial. Okay.
There we go.
So how did you get that to happen?
Okay.
What do you have to do?
Go into the command window and hit enter.
Oh, really?
Yeah.
Oh.
There we go again.
That was a good thing to try.
There's that thing.
Do I keep the graph open? Or do I close the graph?
It probably doesn't matter. It'll just replace the graph.
Okay, so from the long time ago, when we were learning third way to predict future, how do we know what will be the future of the wave function if we know it at the initial time? So here we do have expansion coefficients, they're known. We do have wave function, and the third component which is missed. What is the third component? Just do not make me to doubt your skills. How do you propagate wave function forward in time? Why something is changing in time?
It's time dependent.
Yes. Probably we need some additional quiz or homework, as I see. Movement forwards in time occurs due to phase accumulation, right? There is a time-dependent factor that is evolving in time forwards according to energies, right? Does it look familiar? So, phase accumulation, with, which comes from the eigenenergies. So if we do implement this equation, and then we just plug in the definition for the so here is the time-dependent wave function, and we integrate it over x with x operator. We will get the expectation value of position at each time, right? So it is a little too silly problem for true science, but as a step learning tool, it is very reasonable. So we just need to explore evolving forward in time and then implement the equation for the expectation value. And then some style of visualization. So do not worry, do not panic, everything is already written. You will just run the code. We are going over the details to get an idea of what is going on. If you have looked through the code, you may identify that it looks a little bit different than this writing on the board and things that you saw in class. Please do not hesitate to raise the hands if the code looks a little surprising and not what you expected based on your intuition. Okay, good. So there is a little trick that doesn't touch any foundations, doesn't touch any principles. The only thing is that we can perform multiplication of the conjugated wave function by itself before we evolve it in time, or before we implement this expectation value procedure. So the only thing that may surprise you there is that product saves percent is pre-made. And if you see the conjugated and non-conjugated wave functions correspond to two terms from psi1 and psi2. And if you multiply this thing by itself, so brackets with two terms in each, how many terms will be after you perform the product? 4. Well, sometimes one can simplify. And this phi 1 star, phi 2 star, phi 1, phi 2. And then from here you will see that there will be 4 terms that contribute to our answer. Phi 1 star, phi 1, phi 2 star, phi 2, phi 1 star, phi 2, phi 2 star, phi 1. Please object or argue if you do not like it, if it sounds strange. So we'll need to take this stuff squared with conjugation. And this thing, wave function, contains 2 terms. After we multiply it by itself, there will be 4 terms that contribute to the answer. And each of these terms will also evolve in time according to its own time dependence. You do not need to memorize anything. We will go in details in class. Here, just general guide. So this one will not evolve in time. I times 0. This one will not evolve in time. And this two will evolve in time according to minus I h bar e2 minus e1 times t e plus or minus I h bar e1 minus e2. Right? Because of conjugation, the sign is swapped. So we can just program these 4 terms. When you add together this one, the exponential of minus delta energy is minus delta, this will be plus delta. Because of Euler, this will be simplified into cosine of E2 minus E1 h bar times t. So all imaginary stuff will disappear, and then we will have first, second, and summation of third and fourth. We add them together, multiply them by x operator, and integrate. Right? Good plan. I'm proud of it. And just to have a general idea of the components that we are dealing with, we can plot each of the 4 terms at the beginning, and we can plot the summation of all these terms as function of time, just to overview how the model progresses in time. So this is better than wave function because it has interpretation. It can be either probability distribution or density of electron. Wave function, even if you know it, it is strange because it has complex numbers and it doesn't have direct interpretation. So if you do not care about stuff that I mumble, just run the code, make screenshots, save them into PowerPoint, and relax. You don't need to do anything else. So I was sitting here a little longer than I was planning, and I was entertaining myself by adding the comments to each line of the code. You may do the same if you like, but it is not necessary. If code is working, who cares? But sometimes if you try to read stuff that you are writing years later, you forget what it is. So comments are always good. So let's go through the lines of the code. So you set up the size of the box, you split on the grid points, you set up the increment of position, and then you define, so here's the only input from today's class. Remember this 1 over square root of L, sine of pi x over L. This will be the lowest eigenfunction of the electron in the box. Then the second one is the same with only the factor 2 in the argument. And then you can plot them and enjoy how they look like. Yes?
So if you had a third side or something, would you just be able to put a 3 in?
Yes, exactly, yes.
Okay.
Yes. So if we run it, just show it. In case you have forgotten how sine looks like, right? So the first one has one hump, and it is wave function, it is not yet squared. And the second goes like up and down, right? So what is next? Then we do see from our quick overview of this problem that we will need products of these two functions with conjugation. So first one squared, second one squared, and which can be named as, how can we name them? Like wave functions, eigenfunction squared, probability, distribution, electron density, something, right? Do not hesitate. If it is not great, you can say something wrong, and then by hearing feedback, learn, is it right or wrong? But you see from here a strange thing that is a little bit counterintuitive. So you need to find product of different functions. Psi is 1 and 2. Psi 1 by psi 2, psi 2 by psi 1. Even if you were previously considering some textbooks or introductory courses in quantum, most likely you are not seeing those. And we may name them like transition probability or transition density. But we don't care how to call them, we just know that those terms will contribute to the answer. And if you plot them, then you see square of the sine of the first harmonic will be approximately the same as before squaring, right? The square of the first excited will turn minus into plus with the red line here. And if you multiply these first and second functions, it will repeat the pattern of the second function, being positive and then negative, and slightly adjust the edges. Is it okay up to here? Right? Please stop me. I'm here to serve you. If you do not following, I can go over it again. So what do we do next? What happens if you hit enter at this point after those are plotted?
Plots the next thing.
Huh?
Plots the next thing. It plots the next thing.
But what is the next thing?
Time dependent.
So what is the next thing? Just try and tell it by. Sometimes, if you have all equipment, then scientific activity is nothing but verbalizing what you see. So please perform your scientific activity. What do you see? Oh, okay. We went too far in science and we didn't count technical details. So please give me some secret science if your code doesn't work at all, or if it fails to run. So if it do not look on each other so that no one feels uncomfortable. There should be a match between where you save your code on the disk and the directory where you type commands. So right now it is not very visible. Here it shows at which path the code is located. Like I put it users, my name, downloads, and this P box. And then if I stop everything and I type pwd, so here I'm getting the same path as there. If they are different, you need to make sure that they are matched. You can either do change directory cd and whatever, same type as you do Linux here, or you may want to re-save the file in the directory that comes here. So there are different options how you do it, but make sure that command line access and disk space where you save the code match. You see here the pause command. It means stop and wait until someone hits enter, right? I'll just make a circle around to see if everything works fine, and then continue entertaining you with stories. Now you can verbalize what you see.
Look at those little instructions. Wow. So cute. Yeah. It's probably the mathematical groups. Actually, they're mathematically rigorous. 6. Need to find we've made sure that every and you're not going to see it here. All the
What's your
groups,
operation?
each element is an operation.
Then what are your
So you get an identity. So every group has an identity. And so ours are like spatial operation. We're taking rotations upon axes, mirroring upon planes.
So how, please give me some hint, how do I verbalize what happens on the screen?
2 groups for each one. 1 group. Yeah. 3.
The time dependence is not true.
Of what?
I forget what it looks like.
wiggly thing?
Yeah, was it 1 or 2 homes?
So what do you see? How do you describe it by words?
So then I'm just taking this side times this. Like where it's
Oh, so you didn't turn it here?
which then gives us.
It is time dependent. Yeah. That was what I was sure.
Well, no.
You can't be the superposition first and second step. There would be some stuff there was.
I wish it paused. I need to pause it after this. I'm gonna.
fine.
There.
Oh, yeah.
Oh.
Which one? Yes. That end value coordinates to what usually side.
I think you got it now.
Side one, the end value is one. Side two is the end value is two. So you gotta have the side three.
Look at
Same
that.
equation, same change.
What do you change?
L. Also, I played it.
Wavefunction makes it small. Just shit on something.
Yeah.
Look at these nuclear.
Look at that.
Yes, but it is too technical.
You should recode it.
Okay, so one version is sine functional attack.
Bitch, I just want to see.
No, it's not function, but group.
If I'm being a bitch, trying to keep you awake in a bitchy type way.
So,
Mine there. You know what? No, I'll take this one. Yeah, this one. Taking your place in class.
Okay. I think you'd like that class.
I'm really struggling to keep awake. I just hope that I also don't have no feeling wrong.
Conceptual question. If I take oxygen molecule and I throw in another electron, do you think it's stronger or weaker?
Like, the
The
bond
bond.
between the oxygens?
Yeah.
Probably weaker. Because normally it'd be in its lowest energy state, so you start fucking with that, it's gonna want to break apart, which means bond is weaker.
It's actually not true.
well, you know,
But I don't know
it
the
makes no
answer.
sense why.
This is supposedly though, after I draw this, I should be able to understand more.
Because the oxygen, or the electron goes outside of the oxygen, pushes it in. Goes.
I think it has to do with the bond order. I think it'll come out. From
Yes.
It's probably on Google.
So trading back and forth. This is perfect. What is yours? Yes. So, gentlemen, what is moving? You've told once, I just forgotten.
It's the time dependence of the probability distribution.
Okay, so by collecting the voices, the idea is that what is wiggling forth and back is time dependence of probability distribution. Let's run it once again. So it means that there is a bigger probability to find electron on the left side on the box. Then a little later, there is a bigger probability to find on the right side, and it kind of bouncing forth and back. So if it would be no quantum theory, classical particle, it will just bump into the wall, reflect, go back, bump, reflect again. So it will be a very tiny spike showing where electron is, going forth and back, right? But here, because you know this uncertainty, and it is always like this smooth curves, so instead of approaching exactly to the wall, it starts moving backwards when it is like quarter way toward there, right? And if you do not have language to tell it, you can tell it is time evolution of probability distribution, right? So it doesn't tell anything, but your answers were sometimes much more insightful. But if you just need to quick answer, time evolution of probability distribution. And then you are completely right that something going forth and back, bouncing, and after you add together, after you look onto this evolution over the whole range that you have explored, you can plot it in the same way as London taught us last Friday. So plotting the three-dimensional distribution of two-dimensional function. One argument is position and another is time. And as time passes by, it just goes there and back, there and back. Make sense? I don't know if I asked you to make a verbal comment on this, but in your homework reports, but you may do it. Just explain by your own words what is going on, right? So electron bouncing, quantum electron bouncing from the rules. So this is this symbol, P of x and t. But if we make analogy to true research, true experimental life, you are typically measuring not probability distribution, but observables, expectation values. And here our simple example of expectation value is what? Which operator?
Position.
Yes. So what we do, we basically multiply this by x dx at each time and call that it will be our expectation value of x. So which line of the code this equation is implemented at? Any guesses? So let's look through the code and try to identify where this equation is implemented. So we do have, well, once it is here, and then we set up a cycle over time steps, right? So in the code, we are scrolling through several time steps. We set up this cycle, and then we add together the 4 terms with their time dependencies, as it is shown here. And they're stored in the variable RR, right? And then we multiply this variable RR times position times dx. Maybe in version that were distributed by email, the dx is skipped and then everything is multiplied by dx after the code is run, like it is taken out of brackets. But this is implementation of the protocol to find expectation value. Okay? Very good. Almost done. We are done progressing forward as scientists, but we are not done yet in selling our data or visualizing it. So this equation is practiced at each time step. Each time cycle runs over this point. Right? But we want to see the whole trajectory. We want to have a table where will be time 1, expectation value as function of time 1. T2, expectation value of T2. T3, so line of times and line of expectation values. So we may want to either immediately save to the file, element by element, or we may want to accumulate the data into special assigned variable. So if you look on this, on the next line, you see it sets up an array and then adds one more element to this column at the bottom. So each time you come through this step, this column becomes longer and longer. So it accumulates data from this calculation. And after we are done with the cycle, you can just plot this variable. And it will contain the answer. So how the trajectory, how the expectation value of position depends on time. Right? So let's go forward and see what happens. So how does expectation value of position depends on time? Any observations? It looks like you guys are surprised. Or maybe we all are a little tired after the long day. So the electron balances force and drag between walls. So in some sense, it does perform oscillations, so it's forwards and backwards, right? And this oscillatory motion is because of the superposition, because it is not in the eigenstate. For eigenstates, if you do this numerical experiment, it will stay steady, most likely in the center, 0.5, 50% between the walls. But if it is a superposition, it starts moving. Does it ever approach the wall completely? No, see? It stops like at 68% and doesn't want to go further because it has thickness, uncertainty. So it starts reflecting when it didn't hit it literally, but approaching it, it starts. It's like a flory cat approaching the wall and feeling that he is near the wall because of the whiskers or fur touches the wall. So it goes back. In average, where does electron reside if we average over all the time steps? In the middle, yes, which is like very well expected. So what do? Copy paste images by printing screen, putting into PowerPoint, and then it will be your homework report for part 1. So I will make several circles between rows and give me pleasure of answering questions if you have some. No, same. It goes same.
Go down there, go down.
I did, and they just be struck on.
Well, that's a whole new chemistry.
Yes.
There's no better way. You don't need any more.
That's enough, but
You know, no bigger.
probably can't really go small.
Yeah. I mean, it's got everything too. It's got the number, the abbreviation, and the mass. Wow.
In atomic mass units.
And Daltons, yes. And Daltons.
Dolphins.
Dalton.
Who the fuck is Dalton?
Well, there's no one people just like to say grams per mole relative to carbon 12. But you know, who's getting specific? 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 8. Perfect.
Yeah, look, you're doing quantum.
Essentially.
Spin up, spin down.
I'm making molecular orbitals. Wow. From a linear combination of atomic orbitals. Crazy. And I know that it's paramagnetic because one has a lone pair. Or not, one has a lone thing.
Yeah. Would it be diamagnetic if they were also?
I believe so. My only question though is, since these two are
What about
degenerate, those are different. My only question is, so since these are degenerate, does it still matter that there's one here, or is this now? I think probably because there's an odd number. I think so too. Do you have any homework tomorrow?
No,
That's not one.
that's got my optics test.
Easy?
Yeah, I can't.
You have the easier of the two. So many six are bonded, right?
Maybe 7.
No, definitely six. Six are bonded. Minus the anti-bonded, so 6 minus 1, 2, 3 trying to think of what to say here. So she defined her group without the identity. I was gonna try to make it more complicated. So she defined an open group with all of the elements do not, or some combination of the other elements do not loop on themselves. But I couldn't find a mathematical way to say it, so I just sat there and the joke. So.
Well, it stops simulating. Short period.
Well, you got one squared function there. Squared function there.
Just copy paste. A couple of images and like
maybe it's just. Oh, those must be like the side 1 and 2.
Oh, I'm trying to add a third function.
Excellent, excellent.
So far I'm got it to this point, and I think that's what my graphs should look like. So we're trying to interpret these.
That's cool.
He told us it was going to be stronger, but from this analysis, I've determined that it's weaker.
Any questions about how things work or
Not as of right now.
So for the question, it says finding expectation value, but
Yes.
is that just basically looking at PowerPoint? Or are we like counting that?
Oh, I did it right. Cool. 1.5.
Besides like the fives, it's like.
Yeah, I think oh yeah.
and you see this one?
What's the expectation value?
Oh, what is showing you?
The maximum of all of the outcomes, maximum of outcomes.
So which line, which variable is where? Yes, but it is important to say that it oscillates and never comes to edges.
Each mass of min is when it approaches the wall of the box.
Yes. So this might be a low point, and that may be a line of text. That's where you would probably interpret it. Huh? Oh, that's fine. Okay. No. Okay. You already did a terrific job on presenting. We need relax on presenting for a couple of weeks. There will be more presentations, but not next week and not second week. Maybe third. So you
I guess I'm not really sure how you're wanting us to read the expectation value off of from that one.
Okay, let's open it. So, hit, can I?
Yeah. I had to pause that.
I just. Let me see what. So if you hit once again, and once again, what do you see? What is this figure?
So on the side.
Which
With the expectation value.
which line of the code gives this image?
When you run
Quad.
Yes. Yes. So 1/100 is dx. X-axis is time, and y-axis is the expectation value of position. So you just copy paste this, screenshot this image into your report, whatever, and write a couple of words or a couple of sentences, whatever, how do you interpret it, so that it never approaches the walls, which are at 0 and 1. It is oscillates near 0.5, and this offset approximately corresponds to uncertainty, because it bumped literally into the wall, starts reflecting. Make sense?
Yeah.
How tired or how relaxed are you? Do you have energy for second part? At least to. Oh, someone doesn't. Did you please give me a sign if you need more time for part 1? No? So you're kind of ready. You collected all data and either completed reporting or just prepared everything to complete the report at home, right? Part 1. Good. Good. So part 2. Let me point. So what we have done by now. What we have done by now was dealing with near future in the lecture time, like Friday and coming Monday. Part 2 goes further away. Let's check if we can work with this and understand what is going on. Then everything will be super easy and pleasant. So I'm going to redraw this figure once again. L, energy 1, energy 2, energy 3, energy 4. Make sense? So the energy sub n was some constants. Brain knows which constants, like L square. But right now we do not care. On the nominator there is a n square, which means the higher the number of the state, the larger is offset from the bottom, and the offsets between them increase. Make sense? Please raise hand, attract my attention if I'm telling some nonsense. So, it's fine. Now, suppose that we are done with our oversimplified problems for class and go to real life. It's very rare to see a system that has 1, 2, 3, 4 orbitals, quantum states. Typically there is like 100 or 1,000. And we will not be able to list them, or even if we list them, we will not be able to perceive by human eye and human brain. So suppose that we have a situation when they are much denser, when the E1, E2, E3 goes like very, very dense. Then one needs to set up a way to represent a large number of energy levels into something simple that human brain can understand and analyze. So there is a concept of so-called density of states. So here are the states or levels, and they can be either dense or sparse, right? So one can draw a peak at a certain energy, if there is an energy, draw no peak if there is no peak, and represent each energy by a line, by a peak. Here it will be clear. 1, 2, 3, 4. But if they are very dense, then these peaks will overlap and form some figure. Make sense? So, peak number n. This is the energy. We will set up a function that will give us a peak when there is an energy, and give no peak if there is no energy. And then we add together all such functions. So then all manifold of these eigenstates will be represented by a continuous function. Okay? So I'm asking you just to confirm general understanding. We will go in much details in the lecture material. So this is kind of teaser of a movie rather than whole plot story. Now, please tell me, where did you saw one-dimensional boxes? Raise hands if you touched one-dimensional boxes ever. I did. It is an abstraction. Typically, if you get a FedEx package, well, it can be an envelope, but if it is a box, it typically is three-dimensional, right? Like height, length, depth, three-dimensional boxes. And if the box has 3 dimensions, electrons get quantized in each of the directions. And the equation for this energy becomes a little bit more complicated. So instead of one number, one quantum number, and one length, one gets nx, ny, and z, squared, squared, squared. And here one gets Lx squared, Ly squared, Lz squared, plus some constant, and then energy depends on Nx and Y and Z. So sometimes this writing can induce shock in half of the audience. But if you do not rush, although we are kind of rushing now, it's just adding together. You know that electron can move along x direction, can move along y direction, along z direction, and for each of the directions it can move with different velocities. So if it doesn't move anywhere, we put 1, 1, 1 for both dimensions, for all 3 dimensions, and it will be centered in the box. And this Lx, Ly, Lz is our feedbacks package. Y, Lz. So the box, your birthday gift with electron inside. Okay? So the main idea that if x and y in x equals 1, then it will be the lowest state. Lowest state. And then the energy of the lowest state will be determined by all 3 sizes of the box. Okay? Also, we do not restrict ourselves with a square box. We can talk about box for a rifle, which will have 1 length. Oh, no, yeah, we are so peaceful. A box for skis. So 1 dimension much longer, to another are short. Right? Or we can have a box for pizza that will have 1 dimension short and 2 other long. Okay? Or we can have a box for wedding ring, which will have very small dimension, very small in each dimension. Okay? So there is a connection between set of energies for a box and its dimension. And since the number of levels will be so huge that we will not be able to go through them in all details, one may put here nx, ny, and z, and develop this density of states profile for any box of any dimension. So what we are going to do is to run a code that generates this density of states files for boxes of different aspect ratio. So what you are asked to do is just modify parameters Lx, Ly, and Lz that are provided in the code, look on the generated density of states, record it, and then make some little observations. This will be more than sufficient. Any questions on this general direction? Okay, so I will go over the code quickly. So I will go through the code just for your curiosity, but you can be very successful with this assignment without looking at it. Just run it and watch the figures. Yes?
So you have all these comments to this where you send this one to us? It brings the comments of what each line is in, is it?
I thought I did.
The one you send us don't have the comments.
Oh, for P-box.
Yeah, and that, yeah.
You want it?
I would.
Okay, yeah, I can share. Yes. Maybe after. Now I'm too excited to complete this explanation, and then in the peaceful evening, I will share the comments. So the code is using atomic units. Now, right now we do not need to know about them, but maybe some of you are aware. They're just so nice that mass of electron and Planck constant are equal 1 in this system of units. And then many undergraduate courses have a lot of adverse problems of converting from one system of units to another one. It's the thing I hate at most educational process. If you do with atomic units, and then you just skip this type of problems. So size of the box. So right now it is approximately square, and the units here are atomic units of length, which are half angstrom. So 260 is about 1.3 nanometers, which is very reasonable size for like quantum dot. So the 26 will be 1.1 nanometer. Now it is about 10 nanometers, which is already, so erase previous minute of recording. So this one will correspond to over than 10 nanometers, which for our purpose it will be same as bulk, over 10 nanometers. So for this version of the code, and you see the title is DOS 3D, so it will make for big box with an elephant size box. Now I'm typing this DOS 3D. So please give me little signs if you haven't, if you didn't get picture like this. So everyone got it. So this is energy. So this is bottom of this box in energy, and this raises. It means that if it is a three-dimensional box, which follows this equation, it means the higher the energy, the more states are available. It means it becomes, it is sparse at the bottom, and then it becomes denser, 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 denser. And it is most typical situation. Past this point for high energy, the code is not reliable. So about after 1/3 of the range, it's not data, it is garbage. And we will discuss it later. So each tool has range of applicability. This tool is applicable only here. And the dashed line is something that we will derive in class maybe next Wednesday or next Friday. So the density of states can be derived, I wouldn't say super quick, but relatively simple. Our common skills in the class are well sufficient to reproduce this numerical data. Now, so do this figure, make a screenshot, and let's go to the next one. So if I make one of the dimensions 10 times smaller, I'm coming from a box from square box to pizza box, right? And I can call it, rename the code as DOS 2D. Okay, here I reduce the size in LX. And then I am running the code. You run first and see what, and just report what you see. Otherwise, it will be boring. So, density of states for pizza box, for two-dimensional box. For if you involved in research activity, it will be density of states for thin films. A little hint. Otherwise, it will be not very visual. So we'll skip the way how it is programmed, although we may do it later. So what I suggest, you go to line 37 and you plot only numerical data. So you close the bracket, put semicolon and %, so that you do not plot the theory and make only numerical data. Line 37, plot E range, comma, DOS. Yes. Let me see what you do here. Good.
Ready to go home. You need to do this.
Percent.
Oh, after this.
Save. You may save it under Julie. Save as.
Also, I can't edit any of these PDFs.
So now you're running.
Just the dumbest fucking thing.
Good point. Bring that guy back in here.
What stupid shit.
It's supposed to work.
Should have like Acrobat on here. Then you need to like sign in and fucking pay for it to use it. It's just like, why the hell is this even on these computers? Like, it's useless.
So there's a rotate that.
No, first you want to twist and then rotate it.
I want to do one operation. I need to answer these questions in my mind and get to one of these yellow ones.
No, save.
So is it linear? No.
It doesn't look linear.
Is there two or more rotation axes where you can rotate them 2 pi over 3 or more?
Yes.
I see one. I can rotate it 5, right? 1, 2, 3, 4, 5. I think because it's a.
You could rotate it pi, like with the z
So
axis,
you
right?
have a pizza, you have a red.
Yeah, if I stick it through here, right, or through the top, and
Yeah, you could spin it that way, or you
5
could
times,
just like
right?
flip it.
No, because they're not. This is like top down,
Success?
Yeah.
so the two rings are opposite.
Save.
So you can't do this because then it's not the same structure. But I can rotate it 5 times if I stick it through the middle, right?
Share your success.
Oh.
Very
Excellent. Very successful. Yes. So, how would you describe your success by words? What do you see? Again, you cannot trust the data passed about 2 electron volts. Just share your vision, which geometrical figure or what does it resembles from everyday life. Do not hesitate. Yes, that's a discovery. So any 2-dimensional system will have density of states in form of steps. So if someone doesn't show you nanostructure, a system just shows you density of states, and you do see steps, you can impress your colleague telling, your system is 2-dimensional. So it is a universal property. And we can also probably derive it in class. That's relatively quick. So if you see steps, it is 2-dimensional. Record the image, make a little comment, and now let's try what if the system is instead of pizza box, it is a box for skiing or some. Huh?
I didn't delete that image, I just
Okay. So please try to make one more dimension very little. So just simply remove one of the zeros here, and you can record it as one-dimensional DOS, and I will walk around and see how things are progressing. Yeah, use one of the box sizes, another box size. Yes, save
carbon.
Give me a second.
Not sure what it is.
One dimension.
Square root increase. Spiky. You're right. I was mistaken.
That's very scientific.
Okay, so are there two or more CNs where n is greater than 2? No. Are there CNs? Yes, I the C5. Are there
A little comment to save you a few minutes of your precious time. If you in MATLAB command line, if you type arrow up, it brings up your previous typing. If you hit arrow up 10 times, it will show what was your command 10 steps ago. So instead of retyping it again and again, you can just bring it up.
Are there 5 C2 axes perpendicular to that C5? No, there are not. Or are there? No, there are not.
Are you sure?
Yes, because
This is the energy.
No.
This is energy. Just the density.
Are there
So as we increase energy.
are there horizontal mirror planes?
At some point, it crashes the machine.
Horizontal mirror planes are perpendicular to the rotation axis. So it would have to be like this.
So we probably should
No,
change
because
it
again,
to
no.
27.
So no. I have to memorize this.
Are you fucking kidding me?
No, I wish I was.
It's gross. Why?
Because I'm supposed to be able to do it in a seminar type setting. I'm supposed to look at a molecule and know its point group. I'm also supposed to memorize the first 4 or 5 rows and figure out tables.
So
Gradually gets more, but it's way.
So because you added.
But let's not get into that. So what did I say? I said there's no horizontal mirror planes. Now, are there 5 vertical mirror planes? That might be a true statement. Okay. Wait, no. Yeah, that looks to be true. I'm gonna say yes. Oh, I'm calling it C5.
Yeah.
I can't check.
Oh, you're going to zero.
direction.
Yeah.
I just have it
Maybe
zero.
step ahead.
Long here.
You're ahead of everyone.
Sort of short here and really short here.
Yes.
So it's like a gum.
Yeah.
Your impressive success is indeed impressive. So, how would you describe your success in words? Again, you cannot trust the data past 2 electron volts, but what do you see?
Spikes.
Spikes? Are those spikes symmetric? No. So you see asymmetric spikes, right? So they look. Who is mathematician? Yes. So if you center your system of coordinate at the peak at this peak, which function it looks at most like? So here is your 0, and here goes like this function, x and y. Well, if you're not mathematician, you're also allowed to give suggestions. Which polynomial algebraic function is represented by this graphic?
1 over x.
Yes, 1 over x. So if you see 1 over x features in your density of states, it means your system is one-dimensional. It is very well proved knowledge. So from now on, you can recognize dimensionality of system just looking on its density of states. So if you would take this class 15 years ago, you would get Nobel Prize. Well, if I would teach it 15 years ago, maybe I also would get some success. Do you you know about graphene? And you know about carbon nanotubes?
Yeah.
So if you look on their density of states, which are measurable by scanning tunnel microscopy technique, we can go over techniques later, it's simple. We are doing much more important stuff. One can see these features of steps for graphene and this 1/x features in carbon nanotubes. So since we have more than one dimensions, other dimensions are also there, this pattern is repeated. It's like several 1/x, shifted 1/x. The theory for them, the name for the guy who found them first in theory is Van Hoff. And for carbon nanotubes, CNTs, they are named Van Hoff singularities. Singularities. Because 1/x has infinity, literally, so it's singularity, and the guy is Van Hoff. So if you see Van Hoff singularities, it is either carbon nanotubes or semiconductor nanorods or nanowires. So you are growing as a strong, promising nanoscientist, in addition to your other skills. So what is our next step? Yes. So please practice it just by making all of the dimensions small enough and see what happens. I didn't hit enter. It's still, the image is for one dimension.
So mean. You gotta be so mean, man. I feel like it. But it's so mean.
Yeah, every time I get it, it like
I'm gonna try it. Memorize what this looks like. Tell me if it looks different now.
well, maybe weird.
Okay, that just, that's the thing. It's the thing.
It sure is the thing.
So his are gonna be 26. Okay, I wanna compare with his. 26.
Yeah, that's what I did.
Mine's got more elevation and all this jazz.
What is your number?
That's numbers.
So
26, 7, 8.
you are discovering the
So you get increase.
quantization law.
But you got a big ass
Same
spike.
thing
That's
as
a big ass
later
like
on.
2.7.
in
Yeah,
the class.
but it's
The
unreliable at that
smaller the
point.
box,
Oh, that's true.
the
It's
bigger
2 and
is
2.5.
the energy. So if you make it a little smaller, like 20,
But 2 and lower?
less
At 2
energy.
I have nothing, and you have some shit.
Right.
Oh, so why doesn't anything show up when you're approximate opposite one by one?
One by one, it means your first ground state energy you like have. You be 20 electron volts. And we are not showing this range.
Oh.
Oh, that makes sense.
Okay.
That's right.
Yes. Yes. Good. Good. So I hope to have the same figure as you guys did. So it is very, very linear, right? Instead of the continuous curves, it shows lines. Why? Because when we have quantization, when we have this claustrophobic electron pushed by walls, it has ground state energy very high. And other non-ground state, excited state energies are also very high. So we are coming to limit closer to one-dimensional box. It is a little bit more complicated, but offsets are really big if the box is small. And you can see the control. So right now we are pushed by 0.5 electron volt. So it's still the change corresponds to infrared. But we can push it further if you make these numbers smaller. Like remove this. Numbers a little smaller. So what I'm going to get, the energies should shift to the blue, to higher energy. See? From point 1, it moved to about 1 eV, right? So it is the main message that we discussed in class. By tweaking size of the box, you can get any transition, any frequency, any color of the material by demand. So it will give me a red quantum dot. Just, oh, okay, just grow it a little bigger in the synthetic procedure. Most of you guys are much better synthetic chemists than I am. There are some like keywords like Ostwald, ripening. So please save the image and make a brief comment. How do you interpret it? The program is done. You are free to go, and you can bring the completed reports next Wednesday in class. Even if you are ready to give them to me now, I'm not ready to read them. And it will be kind of your security from getting another homework assignment for a week. I will stay here, browse around, circle around tables and check if you have other questions out of curiosity. But formal part of the meeting is complete. You are free to adjourn.
Rematch here. So you did 21, 2, and 3.
Mm-hmm.
What?
Why?
Is it something to do with like degeneracy? Are you trying to
I want to avoid shift to lift the degeneracy.
So
if you make them equal, it will be like 3 peaks merged together and will be higher height. But I want to see more control and. If you increase the width, then they will be merged together anyway. Width, there is a width parameter. How wide is the peak? Like sigma. 0.025 is approximately room temperature. And the number that in the code that I distributed is like 2 times bigger, which like
I'm just putting everything in.
how much? 500K. Okay.
So when you increase the temperature, the
Width of each line increases because of the nuclear degrees of freedom contribute. We don't consider them here, but in nature they are.
So basically, just grab copy pen.
I'll be there.
And then move it to run here.
you have it on your computer.
I got pictures. I do a bunch of stuff in this lab. Is it huge assist or doing an optics lab?
Gross. But it was hard.
No.
Yeah, it was hard. How's your partner?
It's good. He's actually one of my students in the physics lab.
So yeah, it was the one that did the saving.
How's that?
It's fine.
Yeah,
Okay, want to help me save? I won't fully remember.
yeah, when do what you showed me, how you just type in save, 'cause it won't save it.
Wait, did you say he was or is?
Was.
Only access at math.
That's what